Hi everyone. I want to add a quick bonus video just to tie together the explanation of Levenstein at a distance. I think there's an idea that maybe I didn't make fully explicit that I think might help people sort of get a bigger picture of what's going on here. So you can think of this as sort of a coda to our story. Coda is a fun word. It comes from the Latin word meaning tail. So like if the story was the dog, this is the tail of the dog. So hello from the tail of the dog. So the sort of like the final end of the day 9 videos was us defining this Levenstein edit algorithm, which I claimed would be minimal by making sort of these minimal choices all the time. But it's sort of a weird function, right? If we go back down to what I defined there, like it's returning boop, boop, it's returning a list of edits. But like who cares about that list of edits? Like we've got the target right there. What does it matter? What we actually care about at the end of the day is the cost of those edits, right? If Levenstein returns a minimal list of edits and we get the cost, that cost will be a number. And that number is the edit distance between the source and the target. So it'll look something like this. Right? Now this function, this edit distance, this is a measure of how far apart two strings are. So for example, I would expect when your solution is correct that, for example, edit distance of DNA source to itself or anything to itself, well, this should be 0. You shouldn't need any edits to get back to yourself. Um, the edit distance from DNA source to DNA target 1, where we just substitute the one thing, well, that should end up being 1. Right? So this number then becomes a proxy for how close are these things together, where 0 means no distance at all, they're the same. 1 means pretty close, and like 1,000 means like, oh wow, those are pretty different. Right? So this edit distance function is the actual function that somebody wants at the end of the day. Now, to implement it, you needed Levenstein, right, to be able to get these edits in the first place. Now, okay, an efficient implementation of this, and this is what you see on the Wikipedia page, will fold these two computations together. Rather than actually computing any list of edits ever, it'll just say, here's the cost, here's a number. And I think that's great. That's an awesome implementation. It's the fast way to do it. That's why they use these matrices to quickly get these numbers. It's super clever. It's a cool algorithm. But by defining it this way, by making the edits explicit, later on in about 3 weeks, 3, 4 weeks, we'll get to be able to prove that our Levenstein function is not only correct, right? It always produces valid edits, but that that list of edits is minimal, right? And then with those proofs in hand, then you can know something about your algorithm and sort of like prove like, oh, well, then my edit distance function is the same as a function that does all the computation in one go, and now you've got a nice function that's sort of efficient and optimal. Um, that's the high level approach of what's going on here. Is the goal to get this function, and we've gone about it in a roundabout way. Hopefully having this in the back of your head is sort of clarifying, like makes the picture a little bit clearer. I'm going to try to mention to y'all to watch this video earlier rather than later, though you won't necessarily understand all of it up front. Sorry for that confusion. I feel like the story here got a little muddled in the details. If you have any questions, get at me on Zulip. I hope it's a fun day. Cheers, y'all.